who really was brilliant in coming up with these techniques. And I'm not particularly making a point with the content here, but I'm more kind of using this to tell a story and introduce some concepts of complexity mathematics that Michael has been using. So, well, we have requirements for ISNs, which starts with ISNs should change all the time. ISNs, by the way, are in TCP, you use sequence numbers to look if two packets are, well, following each other, just to maintain state. Well, an ISN is the initial sequence number, so you don't want to guess that, because otherwise people who don't see the data can hijack the connection, which has been known. Yeah, okay, so I think in 1994, this ISN thing, it wasn't known when the protocol was designed, but in 1994 and before that in 1988, I think Robert Morris was involved with that. People started thinking about what are the possibilities if we are able to guess the ISNs. And they figured out it's possible to do IP spoofing. Later, Kevin Mitnick popularized this technique, and people writing books about this whole thing. So the story goes that he broke into the San Diego Center for Supercomputing by using an IP spoofing attack on our remote shell service. And well, since then, because this kind of bug or this kind of problem that IP spoofing is possible became really popular, vendors have added code to make their ISNs more secure, and especially since Nmap provided for some kind of measure if the ISNs are secure or not. So if you have measure, vendors are going to go ahead and try to get better in that measure. So it would be reasonable to assume that in 2001, where those bugs have been heavily exploited, where they still exist, or were thought to still exist, and not there where they were thought that they already had been fixed, you could reasonably assume kind of that those TCP IP stacks would be fairly secure already. But no one ever checked, no one verified it. So Mikhail came up with this idea of just basically let's make pretty pictures. Yeah, let's use things we know from fractals and so on for visualizing the strength of various sequence numbers. And this is called a phase space or state space. So you're mapping the closeness of, or the dependency of one value of a random function or any kind of function on previous ones. So you're trying to find out, are they related, just visually. So if we look at some demo, can we dim the lights slightly? Okay. Well, you should see there are more than the two strongly visible white rectangles there. You have points distributed over this space, over this phase space. And where many points hit near each other, on top of each other, it gets lighter and lighter and lighter. So the black places are the ones that haven't been hit yet. And we are looking at a random function for initial sequence numbers in TCP right now. So if we look at Linux 2.2, we have a fairly even distribution with it doesn't cover the whole area and so on, but it's fairly evenly spread out, which is good. We can't prove it's secure with that, but we can not prove that it's not secure. So we can keep on trying and changing the functions we use to visualize and so on. So if we look at Cisco iOS, we get pretty pictures. You have clear attractors, so it's definitely a lot easier. You need some more analysis to really be able to tell the numbers. Mikhail has been doing this. You can just, if you search for Mikhail Zalewski, you will find those ISN, his research on ISN numbers. but you can tell just visually where problems might be. FreeBSD 4.2. HPUX, it's horrible. It looks really pretty, I agree, but it's a very, very short area that is covered. And then we have IRIX. I mean, yeah. Next, so Windows NT 4 Service Pack 3. I mean, it's pretty again. There's some stuff up there also which you don't see because of the projector, but it's spread out, but it's really easy. So Windows 95, it's horrible, it's very easy. And here's the funny thing about Microsoft. You need Microsoft jokes, you know? So in Windows 95, we have this distribution. So Microsoft is the only vendor who, in 3 years of work, actually managed to, well, fuck up their implementation more. And you can do the same thing with any kind of random numbers. You can do it with DNS resolver, like glibc. You can do it with various DNS servers. You can, with any kind of random numbers. It might even be, you might try it on a poker website to just find out, are there real random numbers behind that, or can I guess? So. And Dan Kaminsky has been using this technique after Mikhail first released this for a while too, so it's really cool visualization. So the basic thing, the common thing we have in all those pictures is we have certain attractors, however they look. They could look Mandelbrot, it's like fractals, it doesn't matter. Just think of it as attractors in a complex system, like any complex system, like the real world we live in. Like a game of Go or chess, I mean, it's a bit different, but it's models, like behavior of molecules, stuff like that. You have certain patterns, certain things happen more than others. Yeah, Microsoft DNS server is pretty fucked up too. This is 2001, so there was another test later. I don't have those slides there right now. Some things improved, some didn't. So, well, and if you read a little bit more about those complex system stuff, you find out strange attractors are an inherent property of complex adaptive systems, which means self-organizing systems and self-creating networks and all that fancy stuff that has come up in recent decades. So, the way I see it in software development is we're dealing with a complex problem, and we have a certain problem that we want to solve. We want to write a certain kind of web application. We have a general idea what we want, and we have a certain kind of set of tools that we are using. And if we combine those tools with our problem, then there are certain intuitive ways to solve it. So sometimes, for example, in C, it's very natural to just use character arrays for storing user input. So we just do that. There's an intuitive way we use this tool. You might use something entirely different in a different programming language. And if we map this together and just imagine this as a kind of terrain, certain things happen all over again. So we cannot easily visualize it, but this is what I think about it. Like, you have a second. I'm still a little bit tired from yesterday. So, dark lab party. So, good one. So, what I'm thinking here is basically, if you look at a web app, if you do pen testing, I think most of you have tried some kind of SQL injection attacks and stuff like that, just seeing if it's possible, just taking a field value, putting what's it called, a bracket? No. A quote mark there, just to see, is there an SQL injection there? And we do this all the time. I mean, companies are making money by doing this, which Yeah, so you just look, you put one quote mark there, and you get result, oh, Microsoft SQL Server, blah, blah, blah. So, and then you start exploiting, start owning this host. So we have a fairly good idea, intuitive, of this terminal, where the problems are. We can try it out. So on the other hand, people who are aware of security have a good intuitive feel of where the security problems are in the code. And they try to avoid it, and they try to check, and they try to work around it. So I think it's possible for people to write better code, like just if you have good programmers, but I don't think it's the most perfect solution because there are lots of programmers who are not good and don't have this intuitive feel whether this intuitive feel of where the problems lie. So what I'm seeing here is there, you see those red things. I don't know what to call them, but they are walls. They are protecting us from certain holes. So if we had certain abstractions for memory management, for example, moving up to a high-level language, you very seldom, or you almost never see a buffer overflow in user code in a high-level language like Python. So what I'm saying is, if we want to help or to create more secure software, we need a certain way to verify that the software becomes more secure. And we need strategies to actually prevent bugs from being introduced to the code, not just hoping your educating programmers will help. Yeah. Okay, I basically already made most of those points. So you have null pointer dereferences, memory leaks, double freeze, format strings bugs, and so on. And those bugs very rarely creep into higher level software. So Perl recently has had a format string problem, but it's fixed. You fix it once. You fix the format string problem in the Perl interpreter, and afterwards, no Perl code should have this specific bug anymore. Another big attractor, problems you just see in many, many languages, is, for example, if two commands or two codelets with like just a sequence that has a meaning in a programming language is very close to something with a different meaning. So it's just one character exchanged or one character forgotten. Then it easily happens that a typo changes the meaning of the code. The same thing happens in natural languages. So yep. So I'm going to stress this further. I kind of have the feeling I have been convinced that there is more to writing secure code than just, well, not making bugs. So, but I'm going to present one more example to just show why people make bad software. And for that, I'm going to look at ESN1, which is a notation standard which is used in lots and lots of software and in lots and lots of security critical software. So just thinking about the applications where I've encountered ESN1, it's a simple network management protocol, voice over IP, H323, SSL, transport layer security, so HTTPS and so on. And TLAN manager, of course, the ESN1 compiler, SMIME, IKE, Kerberos, LDAP, and SMP. But you should also know that the telephone system S7 is using it. It's used in air-ground communication, in flight. It's used for tracking UPS packaging, or was it FedEx packages. The military is using a lot, so ESN is everywhere where critical software is. So, well, I just took it away, but just guess how many of those applications that we know, that we come into contact with without contacts to military or some specialized company software, just guess how many of these have had security problems. All of them. So I'm just listing I'm just giving a partial list of security problems.
Short question. Are you talking about bugs in ASN1